Hello guys, this video also it's very spontaneous. I would like to show you a new experiment that we make, which is very interesting. So we have the space-time antenna parallel connected with the flash matrix here, up and down. We have two capacitors, 16 volts only, and we connect 1, 2, 3, 4 LEDs, 12 volts this time, in series, okay, from one capacitor to the other capacitor. What we're going to do different here is this. We're going to take from this signal generator from channel 1, which is this top channel. Now it's off. I'm going to switch it on in a while, but it's going to be only 1 volt from peak to peak, okay? And we're going to play with the frequency. Right now it's 11.1 megahertz, okay? We're going to play with the frequency first. And this 1 volt is going to come from this channel 1, and it's going to enter inside this device. This device is a power amplifier which can amplify radio frequency, and for example in our case it's going to be like 300 milliwatts approximately the power, and it's going to make it up to 5 or even more watts. Now in order this power amplifier to work, it needs to have additional separate DC supply, which is 12 volts, which is connected here, and this DC input is going to come from the DC power supply. Right now you can see that it's consuming 7.4 watts, 0.6 amperes, 12 volts. So once we amplify the signal, we're not going to feed it directly to the space-time antenna, which is this bigger sphere, but instead we're going to feed to this coil. This is 9 loops of insulated copper magnet wire, 1.6 millimeter thickness. It has 9 loops. And before that, so once we amplify the signal is gonna come here inside this device. This device, it's very interesting. It's power meter. It's measuring the wattage, the power of our signal. Not only that, but here it's going to show us how much is our input signal that we are going to supply to the antenna, how many watts, and here it's going to show us how much of that power in wattage is going to be reflected back, or in other words, cannot be absorbed from the antenna. So in our best interest is here this number to be very small. We want all the power to be absorbed and no power to be reflected. If we achieve that, if all the power is absorbed and nothing is reflected, this number here is going to show our VSWR, which is going to be equal to 1. If there is no reflected power, this is going to be 1, which is ideal, which means that all the power is absorbed, which means that our impedance between the input and the antenna is the same, and all the power is absorbed from the antenna and is radiated from the antenna without reflection. Okay, so this is why we're going to play with the frequency to see where we have resonance and in which frequency we're going to find VSWR as much close to 1, and we're going to see also how much power is this we're feeding, and then we're going to see our output. Our output is going to be in DC, because the flash matrix, it will convert it into DC power. And we have here the LEDs, 4 LEDs as I said, and they're going to flash, and we're going to see the brightness of them. And again, I repeat one more time, all of this we're going to make it with only 1 volt from peak to peak, which we're going to amplify with the amplifier, move through to the measuring device, which is measuring the power, see how much reflection we have, what is our VSWR, how efficient we are, and then we're going to see our result here. But at the same time, not only we will see how bright are those lights, but also we're going to measure with oscilloscope what is the DC output between those two capacitors. So it's a pretty complicated stuff, but at the same time they're very simple. Now, in order the show to begin, let me switch on the channel and see if we have lights in the DC output there. Yes, we have lights. Now light is pretty intense. Here this is 12 volts, 4 in series. Right now we have 1 volt here with 11.1 megahertz sine wave. It's amplified, it's fitted here, and we read VSWR of 1. Now depends how close I go, or maybe I need to increase the power level a little bit. And because this device, yeah, I increased to 2 volts right now. This device usually works best in the range after 5 watts, above 5 watts. So in other words, if we have bigger power, it's reading more accurately. Okay, let's make it 3 volts or 2 volts. And this thing is very sensitive because my body is like a virtual ground, like create different capacitance, different in a sense capacitive reactance with antenna. Depends how far away I'm from this antenna, because it's a huge device, and this it creates also can change the results. Now again, we have 2 volts input. We amplify these 2 volts with 11.1 megahertz. We have the VSWR about 2, okay, about 1 point something, it depends. Let me change the frequency and see. If I increase the frequency, we have very different results, okay. You can see the 6 here, this is the power we supply, this is the reflected power, so only 1 watt is absorbed. All this is reflected back, and that's why the VSWR is very big. So if I lower the frequency and we go back to 10, 11 megahertz, let me go down to find something. Yeah, this thing is very sensitive. So about 11 megahertz, we have a VSWR which is 1 point and something. So sorry, this it's the power that arrived to the antenna, and this is the power that goes back, and all the rest it's used from the antenna. So this is how these things works. Now the lights are on, and the probes here for the oscilloscope are measuring here 23 volts DC, a little bit more. This fluctuation, this noise of the DC, it's pretty wide, it's 9.2 volts, and this is the RMS, the root square of this fluctuation of this peak voltage. But the DC, it's 23 volts. I'm afraid that I can burn the capacitors. They're hot a little bit. No, actually they are not. They are pretty cold, but before that I already burned one LED, and I'm afraid to not burn more LEDs, because the previous capacitors, they were hot, but right now they are not. They are actually even cold. Okay, so this video, what I'd like to share with you is that we can measure the real power in wattage that we supply inside the space-time antenna to the space-time antenna in watts through this power meter. I don't know how accurate is this, but still it gives us a clue. And then I need to measure here the output with power meter or in a different way to see and compare the power levels between the input and the output, to see how efficient these things work and how much power actually comes out. And one more time, right now it's 2 volts, 11.1 megahertz. I can make here a square wave if I want. The power is going to be a little bit more, actually a lot more. You can see now it's 6.5 watts. If I go to sine wave, it's going to be 1.8. So this is something I notice when I change the square wave here. The power level, it's huge, and this because the pulse is very distinct, it's very clear, and this device are actually working with pulses. So the pulse of the square wave, it's much more clear, much more distinct in a sense from from the sine wave. So this is, let me lower the voltage to 1 volt. No, it needs to be about 2 volts in order to be activated. So yeah, have a look now. We have 7.5 watts input, a reflected power 0.59. It's going back, and we left with clean 7 watts power that arrived and that is used from the antenna. This is 1.8 SWR, VSWR, and from these two volts, this is the result in DC. But have in mind something else, that here they arrive right now about 7 watts, 7 point something watts, but here we have supplied to the power amplifier already 8.7 watts. It's going for, in order this device to work. So this is also, we need to include this power and to add it to our input, because it's something that we consume right now. Okay, so I'm very curious to see what is going to be your impression, your comments, and what do you think about this. Again, right now we measured here 27, almost 28 volts DC. From peak to peak, this noise, it's very wide, it's 13 volts, and the RMS of this fluctuation, it's 4.4 volts. This is pretty interesting. I would like just to show you how, once we change the frequency, the power there that will arrive to the antenna and the power that will be reflected, and the VSWR, it will change significantly, very quickly. You can see right now. You can see now we have, let me put it that way, now we have 6 watts coming to the antenna, and almost 6 watts are reflected back. So we have VSWR of 40, which means that it's very inefficient in this frequency, which is only 500 kilohertz below. We go back, and also you can see here the DC voltage. When I change the frequency, it's going down. Okay, our input, this is our output, this is our input. Our input is AC, our output is DC. So when I change the frequency, it's going up, and you can see like that how with the frequency we can increase the DC output to the most efficient point, the resonant point. It's very exciting, and it's very cool, because these resonators, they might need a little bit more power in order to increase significantly their efficiency. We do not know that. We need to increase the power input and see how they're going to behave with higher input power, because this may change completely differently the way they behave. They may increase the efficiency much more. We need to explore this idea with the power of the input, because right now, before this video, I was supplying power from here, AC from here, radio frequency from here, but this device can only supply about 0.3 watts, 1/3 of a watt, which is very low power. Okay, and this device can amplify that power, so it can make it higher. Now you can see I have 7 watts of power from 2 volts square wave. Again, if I make this a sine wave, you will see, let me show you like that, you will see the power level drop significantly. It's from 7.5 to 2.3. Okay, change it, and it's immediately, and you can see also the lights, maybe you can see that. So this is very exciting. The lights are actually working also with 1 volt input, and they are pretty bright, but you know, if I increase the voltage, they increase too much. I'm afraid to not burn them, so I'm going to leave it like that. up to 2 volts. Guys, this is what I was thinking to show you in this video. Again, this thing is working only with 2 capacitors, 4 diodes and 4 LED lights. We can hook more LED lights here. I believe that with these 7 watts we can hook much more LED lights and they're going to work fine, keeping the same intensity. But this is something maybe we can explore in the future videos. So thank you very much for watching, guys. Happy to see your comments, happy to see what is your perspective and what do you think about it, and I will see you again in the next video.